Medical Association leadership in the state lists of
above 10. That's
Reduce the volume more. Reduce the volume. Today we want to look at ANOVA, understanding ANOVA. Reduce the volume. We want to look at understanding ANOVA, and we have been hearing ANOVA. ANOVA means analysis of variance, and this is a method used to compare 3 or more means. That is, when you are comparing quantitative variable, which you summarize as mean, between 3 group, 4 group, or 5 group or more. We use ANOVA. We quickly look at some background information. Why we cannot use student t-test or t-test to compare more than 2 means. I will quickly look at some things, and the logic behind the ANOVA is quite interesting. When we are comparing mean, comparison of mean, you may have 2 means or you have more than 2 means. Unlike comparison of proportion, where you use chi-square, whether the group are 2 or 3 or 4 or 5, you use chi-square.
Okay.
But when it comes to comparison of mean, hello, can you hear me? Some people are making noise. Is it that you cannot hear me? So, for comparison of mean,
no, we can hear you very well.
How you compare? Okay, how you compare 2 means differ from when you compare 3 or more. We learn. We have, the last 2 weeks, a couple of weeks back, we talked about comparison of 2 mean. We discussed t-tests. When the data set follow normal distribution, we have different type of t-tests. One sample t-test, independent sample t-test, and pair sample t-test. But when we cannot assume that they follow normal distribution, we have non-parametric counterparts of all these different type of t-tests. But today we are looking at comparison of more than 2 means, that is 3 or more. So when you're having 3 or more groups, you want to compare the mean. Of course, you can as well, not that you cannot do t-tests, but of course, t-tests only compare 2 means. So you have to arrange those groups into, you have to pair them 2, 2, 2. So the number of groups you have depends on the number of possible pairs you can get. And we're going to look at that. And why it is not appropriate to now conduct t-tests, you will see, because of what we call family-wise error. Now, before we go into that, let's look at what does this ANOVA mean. It means analysis of variance. When you are comparing 2 means, it's clear, very clear. You are comparing 2 means. But here, you are not comparing the means. You actually analyze, though you are comparing it, but how do you compare the means? You analyze the variability. That's the most important here. When one of the conditions for using parametric tests is homogeneity of variance. And we look at that when we're comparing t-tests in 2 means reducible. So now, in comparing more than 2 means, you analyze the variances. And when we talk about variance, we remember measure of variability start from deviation, the square deviation. The mean square deviation is the variance. The square root of the variance is standard deviation. So all of them is still the same, because variance and standard deviation is like water and ice block. If you freeze water, it becomes ice block. If you melt ice block, it becomes water. So when you square standard deviation, it becomes variance. When you find the square root of variance, it becomes standard deviation. So you can get TT back. Well, like the person that you met your husband, you get your water. If you want as well, you freeze the water. So it's a group analysis of variance, is a group of statistical method employed to compare means of 3 or more groups. We have said it. It is good to understand t-tests are not used to compare means of more than 2 groups. And therefore, it is good to have an understanding of the concept of family-wise error. It's because of that family-wise errors we cannot use t-test. T-test is not appropriate. Let's look at what you mean by this family-wise error. Now, when we carry out our hypothesis test, we arrive at a probability of making type 1 error, which is the p-value. Another way of saying is the probability that the observed difference or observed value, the difference you are observing, is due to chance. That's the probability. It's the probability of saying something is there where there's nothing there. If it is due to chance, that's what is chance. It's not actually what you are seeing. You see that this value is higher than this value. This urban is higher than rural. That's what you are seeing. Observed, you can see the difference. The observed difference, the probability is the chance of that. It just happened like that. It's not actually a true difference. It's the p-value, the probability of making that 1 error. That is rejecting no hypothesis when it is true. You can easily say, oh, because I see this difference. Oh, there's no hypothesis that said there is no difference. I reject you. There is a difference. So when no hypothesis is true that there is no difference, but you now reject, so no, there's a difference. It's an error, type 1 error. That is the probability of making that is p-value. So what we are looking at here is the increase in that probability of making type 1 error when you have to do many tests. The way to conceptualize it is this. Let's start with the simplest one. We know that when you have 2 groups, you are comparing, you use t-test. But when you are having 3 groups or more, use ANOVA. Then let's start with 3, the simplest. If, let's say, you have 3 groups, you want to carry out t-test for 3 groups. 3 groups A, B, C. In how many ways can you combine 3 groups? You can combine it as A plus B. You can, if you have 2 groups, 3 groups, A, B, and C. You can combine A and B and do t-test. That's 1. You can combine A and C and do t-test. That's 2. You can combine B and C and do t-test. So if you have 3 groups, you have 3 different ways you can pair them. You can make them 2. So in that you carry 3 tests, 3 t-tests. What you are not saying is that the probability
yes, thank you. Thank you. I don't see them.
You making an error, say something significant when it's not significant, it's higher. Somebody is making, I don't know.
Mute the person centrally.
I muted the. So the probability of you is just like what they do in medical school. When you have many, because when you are doing exam, you have a lot of questions. The comment can be up to 500 MC multiple choice or whatever, yes or no. They know that if you have large volume of questions like that, if they don't remove negative, give them a negative. No, the thing is true or false. If you are gambling, even somebody that if you go and bring your grandmother in the village to come and do the exam, it will pass, because even if they just gambling, because you have large volume of questions, and you will likely have 50, which is the pass mark. And that is why when you miss one, they penalize you by removing mark. Now, the logic behind this thing is that whenever you carry out many tests, there's a probability that at least one will be significant. If normally there's no significant difference, see, you are carrying out multiple tests. The way to look at it is this. If you decide to reject no hypothesis at 95% confidence interval level, which is 0.05, which is 5% level of significance, which is 0.05. remove that is the probability of you making type 1 error. The probability of you not making type 1 error is 1 minus 0.05, which is 0.95. The probability of you not making type 1 error. That is the probability of you saying something is there if it is there. So if you now carry out 3 tests, multiply 0.95 times 0.95 times 0.95. Let me, so that I don't waste much time. It will give you a value. When you remove it from 1, look at this. When you remove it from 1, it gives you 0.143. Look at this table. Can you see? The probability of you not making that 1 error is 40% instead of 5. You know, you have set your probability as 1%. Look at it. That's 2 groups. Can you see number? This table will show you number of groups you want to compare. 2 groups. This one I just put here is number of ways you can pair in combination. You know, if you use the formula for combination, what do you mean? How can you? Because if you want to carry out t-test is about 2, 2, 2. So how many ways can you arrange 3 things 2, 2, 2? We have already said, but if there are 3, if there are 2, it's only 1 way, and that's why you do t-test for that one. But if there are 3 ways you can pair 3 groups. That's that you carry out 3 t-tests, and your p-value that you have set at your level of significance that you have set as 0.05 automatically has become 0.143, which is 40%. Something that you set as 0.05, which is 5%. By carrying out 3 tests, it has gone to 14.3%. Can you see? If you carry out, if you have 4 groups, how many ways can you combine pair 4? It's 6 ways. And try it. If you have A, B, C, D, it's 6 ways. A and B together 1, A and C together 2, A and D 3, B and C 4, B and D 5, then C and D 6. So there are 6 possible ways you can pair 4 groups. That shows that you are doing 4 t-tests in 6 t-tests for 4 groups. And your family-wide error will be 26.5. That is 0.95 raised to power 6 rather, raised to power 6. You now remove it from 1, it will give you 26.5%, 0.265. That's why your probability of making error has increased. That is the probability of you finding a difference when there's no difference. You carry out 6 tests, something will be different, that will be different. Even naturally, if there is not going to be different, since you know you are just you are reshuffling, you do it this way, it didn't work. You do it the other way. You have 6 options to calculate t-test in that data set. So the probability that one will be significant naturally will be, even though it's not significant, has increased. That's what we are looking at. If the test, if the group are 5, you can pair 5 groups in 10 ways. And look at, it has increased to 40%. So if the group, let's say it increased to 10 groups, there are 45 ways you can pair 10 groups. In fact, your family-wise error is 90%. Actually, that if you even increase to a level of maybe it will be 1, it's certain that something will be significant when normally, that is all called family-wise error. That is, you are likely to make type 1 error when you carry out too many tests. Many people mistake this thing. They think it's by saying, maybe I have a data set. I carry out chi-square. I carry out, no, I carry out many significant tests. No, that's not what he's saying. He's talking of a particular group, carry out a particular, this one now, when you want to carry out t-tests, different t-tests on a group, since you can only, t-test is about 2 groups. You have 5 groups now. You have to carry out, with 5 groups, you have to carry out 10 t-tests. In that situation, your probably that's family-wide error appear to the, apply to that situation. It's not just that maybe you are doing your study because I do chi-square for age, for sex, I use sex, I use this one. They say that it's not that one. Some people mistake it. It's talking of this special case where you have many groups and you can now combine the many groups in different ways to carry out a particular test, the same test. So there will be family-wise error, and it applies to this situation. Now, the intelligent people look at the logic of what because I don't like why I try to explain before I take you to this formula, because I don't like, because the real situation comes before formula. It's not formula before the situation. What the formula you see here, the family-wise error just say, okay, 1 minus the probability of you not make it at 1 error. The probability of making it, if you have set your p-value at 0. Your level of signal at 0.05, which is the common one. So the probability of you not making it at 1 error will be 0.95. You remove from 1. So the number will now multiply that in 0.95. You will now raise multiply by itself the number of ways, the number of times you are carrying out the test. That is, if you are carrying out test C time, which is 3, you say 0.95 raised to power 3. 0.95 times 0.95 times 0.95. Now remove it from 1. It gives you the family-wise error. Now, what we have this one is this first formula is the combination formula. You are familiar with combination. You remember combination and permutation. Permutation means how many ways you can arrange something. While combination, how many ways you can combine it. So here now, when you say combination M R, what he says is that how many times can I combine n item, number of items in different ways using Haru unit of combination. When we say for the one we are doing now, we are talking about pairing, because the t-test we are talking about is 2 groups. So if I have 10 by 5, I have 3 groups. How many times can I combine in 2, 2, 2? That's what it says. C combination, N combination R. That is, N combination R means N number of items, like 3 number of items. R means I want to combine in 2 ways. It may be 10 items. I want to combine 3, 3. It's different. But this one now, because we are talking of t-test, which is 2, 2. So our Haru is constantly 2. But the number of groups may change. So N combination Haru means if our Haru is 2, that is how many times can we pair N number of items? That's what the formula is all about. N factorial over N minus R factorial over R factorial. And that is what I did on this other table for different groups, for 3, or 4, or 5 groups, or 6 groups, or 7 groups, or 8 groups, or 10. So it gives you the number of ways you can pair is what we have highlighted here. And it's equal to the number of tests you can carry, t-tests you can carry out. And it is, so that one is the N combination Haru that gives us the number of possible tests we want to carry out. Why the other formula 1, family-wise error rate, is 1 minus 0.95 raised to power the number of tests you are carrying out. That will calculate the family-wise error rate. The other thing you may be seeing here that may be confusing is that I just use K. Instead of saying, the general formula is for combination is C, number of ways you can combine. So NR, but we just use the number of items as number of group K. We use K to replace. And since we are talking of 2, 2, 2, so it's paired. 2 is here. So our own formula, we adapt the combination formula will be number of group, number of tests to carry out, or number we can pair to be K factorial over K minus 2 factorial. Okay, this is supposed to be here. 2 factorial. Mistake. 2 is supposed to be in the front. But it will give you the same thing. Now, let's quickly look at, we cannot see that when you carry out too many t-tests, you have family-wise error. And the higher the number, the more the number, Just 1 minute. Okay, I'm doing a miracle. No charge. Now, we already know now that as the number of the tests increases, the family-wise error increases. So that is why people now came with another logic. That's okay. Instead of comparing the mean 2, like that, let's analyze the variance. And that one take us to the analysis of variance. ANOVA is called F-test because it was first described by ANOVA. In our lecture, we talk much about the F distribution. Now, Fisher was the first person. Fisher was a genetist, was a biologist, like you, like many of us here. And because the biologists and the social scientists develop, especially the biologists, then social scientists develop statistics for many years because they needed statistics more than other people. So they contributed most to the development of statistics over the years. It was first described by Fisher. It's the same logic, somehow the same logic with any other test, because I've already said that all hypothesis tests are the same thing. What they look at is to look at the systematic variance over inherent variance, not systematic variance. That is what I mean by systematic variance. It is comparing the variance based on your study, on the different group you have, the variability you have among the different group. That is the systematic variance. It's not divided by the standard error, that is inherent variability, the inherent variance in the population. I think I explained that the time we were discussing t-tests. For example, if you are saying, oh, we have 3 groups of people, maybe you have you do weight reduction program for some people, and you now have people that you have 3 groups of people. Some people you prescribe exercise, another group you prescribe diet, another group you prescribe combination of exercise and diet, or maybe another group is control, you didn't do anything. So those 4 groups now you have. When you now, after they have done all those things, you now measure their weight. You now calculate the average weight for each of the 4. So you will see they will be different. You have the same number of people, sample size, but the average weight may be different. For the 4, you calculate 4 means. The difference you are seeing is the systematic because it's due to what you've done. But there is inherent variability in them. In the sense that even in the population, you may even see among some people, you may say, oh, those people that did exercise and weight and diet, they have much weight reduction. They have less, they have much weight reduction than the other people. But you can still see among them, even though the average weight is less among them, you may see that some of them see way more than some people in the other group that say you think they have the highest weight. Because there are some inherent variability how that is vary in the population. It is when in our statistics, we put the systematic variance as the numerator and the inherent variance as the denominator. We expect if actually our difference is true, the difference we are observing due to the study is true. Since it's the numerator, it should be bigger than the inherent variability difference. When it's bigger, I should know if it's bigger, if you divide it, to be greater than 1. Not only just greater than 1, it will even increase to a critical level and I say, oh, this difference is so much. That is the logic behind all hypotheses, and the same thing with ANOVA. But don't let me talk much to here, just to give you a background for that. F ratio is the more, okay? Just leave that one. Look at this man, Sarona Fisher. Somebody say probably the cleverest person ever. You know, was a genetist, was the one that computed statistical table before the computer came. Was the one that wrote statistical table. Yes, the statistical table we use to look at our p-value, all those things. Now, let's look at the logic of that F ratio. The statistic, the ANOVA statistic is the average, just like the way T statistic is the statistic for the T test. For ANOVA, the F ratio is the statistic. So let me quickly go through the way it works. There's an example here, because I like working with examples, simple example. We have 3 groups of people. We try to measure their libido. There are 5 in each group. There are 50 people, 5, 5, 5. Mind you, we like using in demonstration. It is easier to use smaller sample size for you to understand, so you be able to calculate and understand the logic. But it's the same logic when you run it, because you are not going to be using hand to calculate. It's for you to know the logic and understand how to use computer software to run your analysis. But when we are explaining, it makes sense to use smaller ones so that it's manageable, you can calculate and understand. Not that we'll be calculating with 1,000 sample. Now, we have 3 groups of people. The first group was given placebo. Placebo is just something like drug, but there's no active ingredient there. You'll be taking it, but there's nothing there. It's not doing you, it's like shock. Then the group 2 was given Viagra, which is sildenafil citrate. Low dose Viagra, that is maybe 1 tablet. Then the other group 3 was given high dose, maybe double tablet, high dose Viagra. So you have 3 groups now: placebo, low dose Viagra, and high dose Viagra. And they perform what they normally do, then ask them to rate their libido on a scale. Oh, ask me which scale. Then maybe a scale of 1 to 10. Now, each person will tell you, oh, you have to put.
Maybe I should tell you what happened. Bureau's prisons. So, why don't you tell us why these asked? I will tell you because it's something that people.
Yes, I promoted myself because that's one of the problems. So, low dose, high dose, placebo, low dose, high dose. Now, if you look at this reading 1, 2, 3, 2, 1, 1, 4, that's for the group that use low dose. Then I am for placebo group. For low dose group, is this 2, 5, 2, 4, 2, 3. And the high dose 7, 4, 5, 3, 6, 5. But you can see the average score, average value here. The mean, the average libido for placebo is 2.2. For low dose 3.2. For high dose is 5. That's average. Look at their standard deviation 1.3, 1.3, 1.58, and look at their variances. Then we now have the grand mean. Now, you can see we have mean for each of the 3 groups. You know, when you calculate mean, the measure of variability, variance is how far away, how spread are they around the mean. That's the variance. So when we talk about variance, variability, we have the measure of central tendency, which is the mean. Then how far away, averagely, from the mean, each of the observation, that is the standard deviation and the variance, what they are measuring. So these are the mean, standard deviation, and variance for each of the 3 groups. But you can combine the 15, all the 3 groups to have 15 people here. Instead of 5, 5, 5, you have 15 people. You can calculate the mean of the 15. This is the mean of the 50 people. That is the grand mean. And this is the standard deviation, grand standard deviation, and the grand variance. Now, where we are going now is the measure where the name came from, analysis of variance. Is this table I'm just what I'm just showing you now, sum of square of the individual distribution. Now, if you remember, when we were doing descriptive statistics, summarizing quantitative data, when you calculate the mean, you want to calculate the variance and standard deviation, what do? You first of all remove the mean from each value. It gives you deviation from the mean. And you know, in that deviation from the mean, because mean is in the middle, some value are less than the mean, some are more. As much as are less than the mean are more than the mean. Some sometimes may be equal to the mean. When you remove mean from the value that are less than the mean, it gives you negative value. When you remove mean from the value that is the same as the mean, it gives you 0. When you remove mean from the value that is greater than the mean, it gives you positive. When you try to add all the deviation together, it gives you 0, because as much negative is there, as you have the positive. That is why the summing the deviation does not make any progress. That is why the intelligent people now square the deviation. When they square the deviation, it gives you positive, no more negative. When you now sum it together, we call it sum of square. Now look at what it is. The sum of square when you calculate the divided by the degree of freedom that give you the variance. And when you find the square root of the variance, give you standard deviation. Now it's example deceptive. Before we go into that, there are 3 levels of variance in this data set. The level of variability in this data set. Now you remember that each of the 3 groups has its own mean. Look at it. Each of the 3 groups, maybe I should go back. Each of the 3 groups has its own mean. So that's why we calculated the variance and standard deviation. That's what we call variance within. That's the variance within each of the 3 groups. That's one level of variance now. Variance within each group. Now, you will see something on this table. On this, you will see something. The Grammy, you can add everything together. When you add everything together, you may calculate the variance between, you treat the whole data set instead of 3 groups, you treat it as one. In that case, if you remove each value from it and calculate variance and standard deviation, that is the total variance. Can you see? That's another level of variance. So I've explained variance within each group. We have total variance, but the other variance they have not is in between both of them. The variance between, you know that we have each of them as their mean. Group 1, look at it. Group 1 has 2.2. Mean of low dose. Group 2 is 3.2. Mean of high dose is 5. Now, if you add all the mean together and divide by 3, it will still give you the total grand mean. Grand mean. Either you add all the 50 divided by all the 50 divided by 50, or you have all the 3 mean divided by 3, it gives you the grand mean. But there's a variability somewhere between each of them, each of the mean and the grand mean. So if you look at the grand mean is 3.47. So each of the mean also vary from the grand mean. Can you see? Because if you look at it, you can actually, the grand mean is an average of the 3 mean. So you can calculate their own deviation from that grand mean, each of the mean. Can you see? So the deviation or the variance between each of the mean and the grand mean is what we call variance between. And that is one that explains the difference between the 3 groups. So can you see now, when you talk about analysis of variance, there are 3 variances you analyze. 1, variance within, variance between, and total variance. And the sum of, and the total variance is the sum of variance within and variance within. Now, let's look at this table very well. I've arranged it. Look at it. Serial number 15. 1 to 5 is for the placebo group. Can you see group? Second column, group 1, the placebo group. From 6 to 10, group 2, that is the low dose group. From 11 to 15 is group 3, that is the high dose group. Arrange them. So when you put the each value X, I just arrange all the 15 value there on this third column. Now, these first two, the following two columns, you see X minus bar X. What does it mean? Bar X means the mean of each group. So what we do here is to remove, like for this one now, the mean from group 1, from 1 to 5 is group 1. The mean is 2.2. We remove 2.2 from each value from 1 to 5, this first 5 in group 1. What it gives us is this. From group 2, which is number 6 to 10, we remove the mean of group 2, 3.2 from each of them, it gives you all this value. From group 3, which is 11 to 15, you remove mean value, which is 5 from each of them, they give. You will see some will give positive, negative. If you add them together, it gives you 0. But of course, you now square it. When you square it, can you see what you square now is the difference between each value, the mean of each group and the value in that group. And that is what we call, when we sum it, that is sum of square within. So the answer here is 23.6. Sum of square within is 23.6. The second two, what is describing now, if you look at the bar X minus bar, double bar is the grand mean. No bar X is the mean of each group. Double bar X, 2 bar S is the mean, is the grand mean. So here now we are trying to look at the difference between each mean and the grand mean, that which is the variance between. So what we do here is to remove the grand mean from each of the mean. For group 1, you know, the 5 of them, 1 to 5, is the same mean they have, 2.2. So you remove 3.47, which is the grand mean from 2.2. That's why it gives you the same thing, no, minus 1.27 for 5 of them. For the second group, you remove the grand mean from their own group mean, which is 3.2. It gives you minus 0.27. I see the same thing for 5 of them. And the last one, group 3, you remove their own mean is greater than the grand mean, which is 5. You remove grand mean 3.47 from it, it now give you 1.53 for each, all of them. When you, of course, if you try to add it, it will be 0 also. You square it. When you square it, that is square deviation. You know, this one without square is the deviation, while square is the square deviation. Sum of square deviation is what we see, sum of square. And when you add it together, it's 20.1335. So we have explained now variance within, then the second one, variance between. The last one is the total variance, which is supposed to be equal to the sum of variance between and variance within. So we look at it now. How do you get that? What you do now, you now remove gram. If you look at X minus double bar, can you see? You know the first one is X minus bar. That is different between each value and their group mean. But the second one is bar X minus double bar X, which is different between the grand mean and the group mean. The last one is X minus double bar, which is different between each value and the grand mean. When you now remove the grand mean, 3.47 from each value here, it gives you this. When you square it, it gives you total sum of square. Now, if you have 23.6 and 20.133, it will give you 43.7335. So you will see that the sum of square within plus sum of square between equals sum of square total. That is. Now, you have not, you know, sum of square, you have not calculated variance. How do you calculate the variance? You remember, you now say the sum of square, when you sum it, divided by the degree of freedom. You are not divided by the number. We have already said it. We are not divided by the sample size. We are divided by the degree of freedom, which is sample size minus 1. So look at it now. For this one now, we want to look at the variance sum of square within, between. We are starting with between, which is 20.33. If you divide by degree of freedom to give you the variance between. But you know that there are 3 groups. There are 3 groups. And when you know the 3, you remove 1 plus from 3, the degree of freedom will be 2. That is why the variance between will be 20, the sum of square between over the degree of freedom, which is 2. It gives you 10. Now, the variance within, which is this one, within, W within. Look at it. 23.6 over divided by the degree of freedom. The degree of freedom is 12. You know why it is 12? There are 2 ways to do it. You know, each of them is n minus 1, n minus 1. There are 3 groups. So 5 minus 1 is 4. 5 minus 1 is 4. 1 minus 4. So 4 times 3 make it 12. Or you can bring everything together. And say 15 minus 3, because there are 3 groups. That is, so the degree of freedom is 12 of variance within. So 23.6 over 12, this is the variance. Now, you want to calculate the total variance. If you divide, that one would be the total sum of square. You don't actually need it for any, that's why you don't calculate it there. Total sum of square divided by degree of freedom, which is 14. Because it's going to be 15 minus 1. And if you look at the degree of freedom, if you had the degree of freedom within and between, it will be equal to the total degree of freedom. And you see, 2 plus 12 making 14 is equal to the total degree of freedom. Now, the statistic, the F ratio, which compare the systematic variance, which is the numerator by the inherent variance, which is non-systematic variance, which is the denominator. Which one is the systematic variance here now? The one that is due to the group, the model. So variance between is the one that is systematic because it's the one that is looking at the difference between the 3 groups. So that is the systematic variance, which is this 10.067. And the variance within is the inherent variance in each of them, which is the denominator. So when you add F ratio, which is statistic, would be 10.067 over 1.967. It's going to be 5. So the degree of freedom also, you have to check it in 2 ways. You have to check the degree of freedom for, if you are to be the statistical table, you go to the statistical table, you have to check the degree of freedom for within and between. So the degree of freedom under 12, you go and check the degree of freedom, you go and look at where they meet, you look at the critical value. If you check in on the critical value, this value is above the critical value. There is a difference. But when you run it with SPSS, it brings it out for you with the p-value. You cannot know the p-value with hand. What you can know is that when you discover that the critical value, what you have got is greater than the critical value. In that case, you now know that, oh, your p-value should be less than 0.05. The SPSS will give you the p-value. Now, this graph, I will not explain it here because it may cause some confusion. But we'll explain later, maybe in next, because we are still continuing the series of ANOVA. This is not all. We continue. However, we have a workshop on it this weekend and your coming weekend. That's where you look at the nitty-gritty and run it with SPSS. Look, something. If they not ask you for the formula, solely I didn't put. If they are not ask you for the formula, you know, imagine I started with formula and I say F ANOVA, F is this. You'll be confused. But the formula is very simple. If we look at Mean square between group. Mean square is the variance, you know. Variance is mean square deviation. That is, after you square the total square, you calculate the average. But you calculate the average using degree of freedom, not n. You use n minus 1. So mean square means the variance. Mean square between, if you look at it, is equal to will be sum of s bar minus s bar double bar square all over j minus 1. J means number of group minus 1. That was what we did. 20 over 2 give us this. The mean square within, which is the variance within, if you look at it, is summation of x minus s bar square all over the summation of the degree of freedom for the three of them. That's what gives us this. So F ratio will be this formula over this formula. That is F ratio. If you understand, even if you have to write it down, you can write it down. Once you understand the logic, you'll be able to even write the formula down. So I think we stop here. Later we'll continue there. I think this is a food for thought for us to ask question. If there's any question. Okay. Let me stop here. Any question? There's 122. That's great. Any question? I'm sure somebody shouted. Let me see. Hello, sir. Please, there is a noisy music on one of the participants. Is this one of the participants? So, I think the music has stopped. No question. It's very straightforward. It's very confusing. You can shout your question if you want to ask directly. Shout your question, and I will read. I will not read your name. I just read the question and answer it. And then I got lost around the degree of freedom. Okay.
Thank you.
Thank you very much for the lucid lecture. Okay.
Thank you.
Okay.
Thank you very much for the lecture, sir.
What do you say? Somebody's talk now. Talk. Unmute yourself and talk.
Okay, I
Is it my volume? Just wait. Let me check my volume.
Ask a question.
Okay, what's the question? We cannot hear you. Somebody said I got lost. Maybe I should answer that one.
Okay.
Okay. Okay.
Can you hear me, sir?
I can hear you now. But we are not talking again.
Can you hear me,
We
sir?
are hearing you, but it's breaking. Go on, it's breaking. Maybe there's
slide. Can you hear me now, sir?
I can only hear. Can you hear me? I didn't hear the other
one. Yes, we can hear you.
Okay, sir. My question.
Okay. Well, Tolulope, we cannot hear you now.
Okay, can you hear me now, sir?
I can hear you.
Okay, sir. So the last slide, sir. After getting our ANOVA, how do we know the P value, sir?
Okay. Yes,
Yes, sir.
I explained it. I will go back. I explained it. Maybe you didn't get it. Somebody say the video is measured in ordinal scale. A parametric approach for the test. I know you have talked about aggregate score. At least thank for the lecture, sir. Is parametric appropriate? Okay. Thank you. These are good questions. They are good questions. No, there are three things. I want to consider I will approach your question from three angles. One, you'll be wondering, why should I use something that is the sample size is very small? We like using small something for illustration. It is easy because imagine I have about 300 now. I will be scrolling that, okay, this are 300 people. So that is why it's manageable. Now, if you remember the other time, I talked about robust tests, approach to non-normality. So if something you feel that something is not normally this way, I rely on the robustness of the test So ANOVA is number one robust test. It's number one robust test, so you can use it. And what we do is that for the people that will come for the workshop, you will see that we're going to demonstrate. We use both, or you yourself can go and do it. We'll use somebody's cracking. I don't know. It's something. You use both. Somebody is not muted. So you use both parametric and non-parametric. You use both parametric and non-parametric. You see, you get the same result. So ANOVA is a robust test. You can use it. So, and after all, this one is for illustration also. If it's an exam, I may decide not to use it because some people may raise it. But if it's publication, I can decide to use it. But if you are going for exam, you feel that somebody may raise it, raise the issue, because you don't want somebody, but the fact that somebody raise issue and fail you doesn't mean that the person is right. But because the person have power to fail you, so there's nothing you can do. That's why you do something, you follow them. That's why you are doing your project, you follow your supervisor. When it's come to assessor, you follow the assessor, you finish. When you pass, you can have mind of your own to do what you want to do. So you can actually use it. Yeah, thank you. Okay. Any other one? Okay, I think I've answered the two questions because somebody talked about ordinal scale and this. Thank you, sir, for the lecture. May I use this opportunity to introduce Dr. Buga, Chief Resident Neurosurgical Unit? Great. That's good. UNTH. Oh, that's great. Well, okay, that's Dr. John Guga. That's great. You're welcome, Dr. Guga. Yes.
Thank you, sir.
Okay, welcome. Somebody asked a question before, was asking question about, okay, the last slide. We was talking of the last slide, then the degree of freedom. Let me quickly go back to the slide and explain what I said about the degree of freedom there. Okay, let me go back to where I started talking about. I think it's, yeah. What I said about degree of freedom, you know, degree of freedom usually is entity, one entity minus one. The entity minus one. The illustration I gave when, you know, the problem that we usually have the same set of people, maybe when we had our previous lecture, I gave an illustration. I didn't use 5. I said that if you are going to maybe have a meeting, 5 people are having a meeting, and you arrange 5 chairs in the boardroom, only 5 chairs. The first person that reach the place, we ask liberty to choose from the 5 chairs. You know, he sits on one and it's not good. He can change it. He has liberty to vary the chair he's sitting on. The second person, he has liberty out of 5 chairs. The next person has liberty to vary within, between, or within or among 4 chairs. The third person has liberty to vary the chair is using among 3 chairs. The fourth person among 2 chairs. The last person doesn't have liberty, no choice. He could not vary. It's only the 1 chair that remains that we sit on. It's not the number of liberty you have now. For the fact that 4 out of 5 could vary where they sit on, the degree of freedom is 4. It's not 5, it's 4. The last person has no freedom to vary. So what the logic behind it is that whenever you have calculated mean, average, a parameter. The parameter is fixed in the population. The variable vary. Like for example now, our age varies because the age in the particular population, the average age is constant. In the sense that even you yourself, if you are 1 year today, tomorrow you are older, next year you are older. The age is varying. Even weight varies. Many phenomena vary. Income vary among people. What you make this month different from what you make next month. As well, even if you are a salary receiver, you may have other source of income. So your income go up, go down. So many characteristics vary, but the average is constant. Usually constant. Usually like age. As some people are growing, some people are dying. In a particular population, the weight, many characteristics, the average is constant. Because the average is constant, it has fixed something. For example, now, when you are calculating, when you start calculating variance, because you need mean to calculate variance. You know, when you are calculating your mean, you sum everything together, you divide by the total sample size. Now, when you want to calculate the mean, the standard deviation and the variance, you need to remove mean from there. You involve mean, and by the fact that you have calculated the mean has fixed the whole thing in the sense that when you know the number, you calculate, you multiply by the mean, it gives you the total. Because the mean is calculated from total entity, you add everything together, divided by the sample size. So when you already know that, you can multiply the sample size and the mean to get the total number. So the total number. So when you are now using that particular, you are using mean to now calculate another mean, because when variance is mean square deviation, it's another mean. There is not the mean of the area, it's the mean square deviation from the mean. Look at it here. What I mean by mean square deviation, can you see? Let's just use this one now. X bar or S bar, that is deviation from the mean. This column is deviation from the mean. Then this column is square deviation from the mean. When you add everything together, this is the sum of square. It's only that we don't say sum of square deviation, just a short form. Sum of square means sum of square deviation. Sum of square. Then we now want to calculate the average sum of square, because this total sum of square, this sum of square will depend on sample size. If the sample size is more than this one, it will be more voluminous, even for the same data set, because it will add more to it. But for you to calculate the average, when you have something now divide by the number of entity, that is the one that is constant there. So when you divide by the average here now, dividing by the total number to calculate the average, that average is the variance. That is why they say variance is mean deviation from the mean. Square mean deviation from the mean. That is mean square deviation from the mean. Rather, you have done square deviation from the mean. Now calculate the mean. But it's easier, it's better to say average square deviation from the mean. So calculating that mean, you don't use n, you now use n minus 1. That n minus 1 is the degree of freedom, because all the entities, all of them can vary except one. From the illustration I gave, that is the degree of freedom. So all of them can, because it is what, if you look at the other one, the variable the other one you calculated, everything can vary. That's why you put everything there. But when it comes to now calculating the mean square deviation and calculating variance, because you have already calculated average before, you already fixed the whole thing. So only one, all of them can still vary, but the last one cannot vary. So that is the logic behind the degree of freedom. So if you look at here now, what I just said is that there are two mean deviation I calculated here. That is, there are two, though we calculated 3 sum of square, within, between, total. But the average I calculated here is for between and within. The first one is the between. This one, 20.1335 divided by this degree of freedom. Because that one is looking at the difference between the group and the grand mean. The group mean and the grand mean. There are 3 group means. So that is the J you saw in this formula, in the formula here. J minus 1. So 20.1334 over 2 over 3 minus 1. Because the degree of freedom for that sum of square within, variance within, is 2, because there are 3 groups, 3 minus 1. Then when you are looking at the one within, you put the total here over, for each of them, you remember there are 3 groups. We just added them together, but there are still 3 groups, because within we are calculating within each of the 3 groups separately. We have number 1 to 5 is group 1, 6 to 10 group 2, 11 to 15 group 3. So each of them 5 minus 1 4. 5 minus 1, 4. 5 minus 1, 4. 4 times 3, make it 12. That's why the degree of freedom is 12 there. So you now divide by the degree, it gives you the variance within. Now, you will see that the variance within is the inherent variance in the population among them, while the variance between is the difference between the groups. So our statistic will be significant if we now put the difference between the groups as numerator and divide by the one as denominator. If the one denominator is big, the difference between them is so big that it offsets the denominator, it will be greater than 1. If it's not only being greater than 1, it will reach a critical value that, oh, no. The difference we are seeing between is far more than what occurs inherently within them. And that is, the more the value, the more significant the difference between the 3 groups, or 4 groups, or whatever group, many number of groups. Now, another thing I want to explain, since somebody talked about that degree of freedom issue, if you remember, later we'll still talk about this one. Look at this one now, the total variance. We didn't calculate it here because we don't need it to calculate F, because the F ratio is the variance between over variance within. That is the variance between the group over variance within the group. That's the F ratio. But you can see when later you get to know, as we go on, you get to know that ANOVA and regression are the same thing. They are 2 faces of the same coin. All this sum of square you are seeing now, you will see it in regression. If you have run regression before, you see a table ANOVA on its own, because it's the same thing. You will see by the time we run it in our workshop, we will run the same data with the same data set like that. I run with regression ANOVA, it gives you exactly the same result. Well, we'll be explaining that further, because I've said it many times that the researchers are intelligent people. The researchers that were interested in observational research in those days, they used regression. While the researchers that were interested in experimental research, they will use ANOVA a lot, because those people that were doing experimental research, they try to control for confounder right from the outset. So it makes them to have many groups to remove the effect of concern from the design state. They use ANOVA a lot to now analyze the many groups. Whereas the observational researcher, that because in some situations it's difficult to do experiment, especially with human, they do their observational and now doing analysis and now use regression to remove the effect of confounder. Both of them are remove confounder in different ways. Not know that they're actually doing the same thing. We get to know that. But what I want to emphasize here is that if, let's say, we even calculate the variance, we want to calculate the total variance now, we will divide this 43.7335 by the degree of freedom. The total degree of freedom is 14, because all of them is 15 minus 1, 14. And one thing is that as you see that the sum of square within plus the sum of square between equal total sum of square. It's the same thing with the degree of freedom. The degree of freedom within plus the degree of freedom between equal total degree of freedom. Look at it. 2 plus 12 is 14. So I don't know. Tolulope asked one question. I don't know if I've answered it. Because
my question is on P value, sir.
On the P value, okay. Yes, thank you. And I said, after we have calculated this one, you now go to table. It's only that I didn't bring it out. Maybe next one I'll bring it out. The table of statistical table. The statistical table, just like the way you do chi-square, any other statistic, you look for the statistical table. But you know that there are 2 degrees of freedom that are looking for that. Because here we have, because the F statistic is comparing 2 variances, variance between and within. So the between has its own degree of freedom, as you can see. The within has its own degree of freedom, as you can see. So in the F statistic table, what it does is it will give you put one on horizontal, one on vertical, where both of them meet, where you now check, let's say this is the degree of freedom for between along the vertical within. You now say, okay, if the degree of I'm looking for 2 and 12, and I say, oh, this is 2. and now come to this is 12. Where they meet, I will now see the critical value. When I see the critical value at 0.05, the way they already put in the table will say for 0.05. For 0.01, you will have separate side. So that critical value, I will now see if my 5, the what I calculated, is greater than it. If it is greater than it, that shows that the p-value will be less than 0.05. It's significant. That was those days. That was those days. So the statistical table now will become academic just for historical purpose, because the computer give you the p-value. So you even know if this is less than or equal or greater than 0.05 yourself. If you run this thing now, the p-value is around 0.02 or 0.04. It's significant. I think I've answered your question. Any other question? Let me see.
Yes, sir. Thank you very much, sir.
Welcome. Okay. Thank you for the lecture. It is quite useful. Then thank you for the lecture. Nice. Okay. Systematic variance the same as Syria ANOVA. No. No. That one. What they just mean by Syria, I think it's repeated ANOVA. We talked about that before. It's under factorial ANOVA. When you have many factors, we discussed that. You know, the ANOVA is a big thing. So we'll take it bit by bit. We talk about, it's not systematic variance. Has nothing to do with ANOVA alone. No. I think I explained it from the beginning. Systematic variance is the variance due you have observed in your data set. Even t-test is the same thing. When you say group, the mean for group 1 is 65, the mean from group 2 is 60. You can see the difference of 5. That is a systematic difference. There's a variation in the value. That's what you mean by the variation in the value. That is systematic. The inherent, which is not systematic, is the one that is not due to your study. The one that is in between. I usually give an illustration. I usually use this blood sugar, male and female. You try to compare blood sugar between male and female. You say the average blood sugar for female is 65, average for male is 60. You can now see that 5 different. People now say, women they have more blood sugar than men. But that is the systematic difference you see. Due to the study you are observing. If we want to put it to test that this difference we are seeing, is it actually due to chance or it's not a real difference? It may be due to chance. So in that case, I will not compare that with what the inherent variance. The inherent variance is, for example, you discover that even among the women, you think they have higher blood sugar. Some of them have lower blood sugar than the average for the men, even than some men. Why some men also that you think averagely the blood sugar is lower than the female. Some of them have higher blood sugar than the average for women, or even than some women. Can you see now? So in the population itself, among men and women mixed together, there are some variability. So it is when your systematic variance, what you observe between the group, offset is bigger than what operates with it, and that is the logic between. They're all statistics. So it's the same logic we use for t-test, the same logic we use for ANOVA, for even chi-square, for everything. If you remember, chi-square, we say observed minus expected. It's the same thing. Observed minus expected. All over expected. Observed minus expected. What you observe minus what you get if they are the same. I think we explained. I don't know if I'm able to explain something to that person that has that question. Okay, so the person is clear now. That's great. That's great. Thank you, sir, for the lecture. So I'm trying to see if there's any. So where do we ask to calculate excess total? Sum of square total. Why do we will need it, don't worry. It is not useful here. When we get to regression, R square, you will see the usefulness of sum of square total. No, I've already told you that ANOVA and regression are the same thing. When we get to regression, the sum of square total is useful. Your R square, the coefficient of determination is gotten from that. You will explain when you get to regression.
Yes, sir, I wanted to,
Okay, go on.
you mentioned you mentioned something about systematic error, and then you talked
I didn't say
about the
systematic error. Systematic variance is different from
so
systematic.
systematic variance. I mean, then you talked about then unsystematic. I didn't know what that meant.
Unsystematic means, well, I don't know if the English is correct, but not systematic, either on or none. That is the one that is due to the one that occur naturally. What I mean is that as we are here, okay, all of us in this lecture now, if we are to look at our weight, some men are bigger than some women are bigger than some men. You cannot say, women are, so different weights for irrespective of the sex. But somebody may not say, okay, let's calculate the average weight for men, average weight for women. And now discover at the end of the day, now say, average weight for women is higher than the men. How do we find out that is true? Because we know that even among us, either men or women, there are a lot of variation. Do you get the picture? So it is when that difference we find between men and women by your sample, you can see that this we average for women is 85, average for men is 80 or 82. You now say this difference. Is it significant? It is when that difference is bigger than the one that naturally occur among us, irrespective of whether we are men or women, that we can say that difference, that we can say, oh, women are bigger than, they have higher weight than men. I don't know if you understand the concept now.
Okay, so are you saying that for the between groups, that's the one that is systematic, then the
between, yes, between is systematic, within is the inherent.
So it makes sense that if the systematic, okay,
can you see?
If the systematic variance is, if the systematic variance, which would be the numerator, if it's higher, then it will be significant. Then
if you divide two things of the same value, it will give you 1. So for it to be, we expect to be higher for it to be, so it has to be greater than 1, not just only greater than 1. It can be greater, it can be higher and greater, but it's not significant because it's just a little bit greater. Do you get the vision? But when it's greater and reach a critical level, it's so big. And not say this one, it's just like many things. And if somebody is doing something, you will just neglect. But when now this one is too much, you now say no, this has reached critical level. I cannot take it. Okay. So it's the same thing. So it has to offset. If the one up, the systematic variance is smaller, that shows it cannot even be significant. Because that shows that it's, just forget about it. Because for you to say there's a difference, that systematic variance should offset, should be bigger than the inherent variance. If it's smaller, that shows that just forget about it.
Yes. Okay.
You get it. You get the picture now.
Yes, sir.
That is why the smaller the statistic, the less significant it will be. So until they reach a critical, not just 1, to be bigger than 1. You understand me now? You know, we already said that it's only the non-parametric counterpart of t-test, Wilkinson and Mann, witness in opposite direction. They are the one that the statistic decreases, the difference increases. That's the only one. Every other statistic, chi-square, anything of other, as the value increases, is more likely to be significant. So I want to see. Okay, if I answer all the questions posted to me, okay, yes, I think I've answered. Any new one? So maybe we'll stop here. Any other question? So I keep on. I'm very sorry. By Thursday, God will continue on this ANOVA by Thursday. The video, all the video will be available for you on the website. It will be available. I'm working on, because the issue is downloading, uploading the video. They are very tedious. So I've opened a YouTube for it and link with the website, which you can go and get connected to the video. So from Thursday, by the grace of God, I was targeting today, but you know, the person that is working on the website has known there's some little thing. I will have introduced it to you, but on Thursday on Felile. And I want to tell the people, let me just stop the recording.